Okay, just to give a quick summary of what we talked about with quarks, all right, and just to put it all together, because we talked a lot about these different types of particles and they all have strange names. So I find that for you, it'd be great if you can write this down in your textbook, or not your textbook, in your notebook, and start to make cue cards for the names of this stuff so you don't get lost. Okay, so quarks are elementary particles. We have 6 of them, 6 different flavors of quarks. Plus you have the antiquarks as well. Okay, 6 different, but they're the mirror images. And if I combine the quarks together, I will make particles called hadrons. So hadrons are particles that contain quarks, quarks being the elementary particles. And I have 2 different types. I have baryons, which are always particles that contain 3 quarks. And I have mesons that are particles that contain 2 quarks, where one of the quarks has to be an antiquark. Okay? So baryons such as protons and neutrons, up, down, down. Okay, going back to remind yourself, each of these quarks have properties such as charge and spin and mass. Okay, so the up quark is positive 2/3, positive 2/3, positive 2/3, negative 1/3. That gives the overall charge of a proton positive 1, positive 2/3, negative 1/3, negative 1/3. Overall charge is 0. And the baryon number of these guys is 1 because each quark has a baryon number of 1/3. 1/3, 1/3, 1/3. These are baryons. Mesons have a baryon number of 0 because antiquarks have a baryon number of negative 1/3. Okay, so that's why they cancel out. It's just reviewing what we talked about before. All right, now for charge, mesons, which are force-mediating exchange particles, they all have different types of charges based on the properties of each individual quark. C is charm, T is top, B is bottom, S is strange. So to find those properties, there's a table in your data booklet that has them. Okay, so right now you can stop again, open up that table, and just go through these combinations and see if you can pull out the charge, the spin properties, see if you can calculate the baryon numbers. All right, just knowing how to use that table would help a lot also for these as well. Okay, now mesons, you would never find a meson that has an up and an anti-up, or a down and an anti-down. The reason for that is these particles are the mirror images of each other. So if they came together, they would explode. Okay, so you would never have the same particle and its antiparticle in a particle. All right, they would explode. So that's why these are different. All right, and just to remind you that the properties, which are dictated by the combination of quarks, include charge, baryon number, strangeness, spin. Strangeness only comes from the strange quark. All right, so what can we do with this? Well, in nuclear reactions, we've seen things like neutrons being converted to protons, right? In order for that to happen, the quarks inside of them had to have changed their flavor. All right, so the flavor of the quarks had to change. So an up quark has to change into a down quark. And what causes that to happen is the exchange of a meson, or a force-mediating particle. So 2 protons have to interact, or 2 neutrons interact. They exchange an exchange particle and cause a switch. All right. However, when that happens, when a switch in flavor happens, it has to obey some rules. Okay, the switch can only happen if charge and baryon number is conserved throughout the process. That means before the reaction, everything that comes in has to have their charge and baryon number has to stay the same at the end with whatever is changed. So here from the textbook, I have 2 examples of nuclear changes. Okay, here's a particle, a very short-lived particle called a lambda particle. It's like a giant neutron. And that giant neutron exists for a very short amount of time, and it falls apart into a proton and a meson, a pion particle, a pi negative. That's an exchange particle. Okay, so the lambda particle has a configuration of up, down, strange. So the baryon number would be plus 1/3, plus 1/3, plus 1/3. The baryon number is 1, so it's a baryon. It exists in the nucleus. It's a very large neutron. Okay, now the charge would be positive 2/3, negative 1/3. And if it's a big neutron, I imagine S is negative. Let's go double check. So if I go all the way back up here, let's go to this table. Yes, S is negative 1/3 in charge. So if I go back here, whoops, this is negative 1/3. The charge is 0, okay? All right, so the baryon number is 1, the charge is 0. Whatever happens in this reaction, the baryon number of this has to be 1, and the overall charge has to be 0, okay? So the charge of a proton is positive 1, okay? All right, but everything has to be 0, okay? A pion, pi negative, the charge is going to be negative 2/3, negative 1/3, that's negative 1, okay? So negative 1 plus positive 1 is 0, so that's why the charge is conserved. So when I converted that into a proton, I couldn't just convert it to a proton by itself. A meson had to come with it so that the charge can be conserved. I will have 0 on both sides. That's the reason we have the meson coming out in that reaction. You need that exchange particle to balance charge. Also, for baryon number, the baryon number here is 0, and the baryon number here is 1, so it's conserved. Likewise, this delta particle is a little bit different. This delta particle, let's see here, is positive 2/3, negative 1/3, negative 1/3. It's also like a giant neutron, okay? But it's a little bit different, okay? It also makes the same particles that are over here. So the baryon number is 1, the charge is 0. The baryon number on this side would be 1, and the charge would be 0 for the same reasons up here, okay? Some of these, this particle here is mediated by a force called a weak force, so it's longer lived, and this is mediated by a strong force, which is shorter lived. We'll learn about what that means in the next few videos.